Today, I'm reviewing an innovative research study that perfectly utilizes modern AI and computational techniques to help fight disease outbreaks. As someone who has spent over 20 years in the technology field, particularly AI and geospatial analytics, I'm excited to share cutting-edge deep learning techniques like these that are being used to tackle real-world health crises like Legionnaires' disease. We'll look at the key findings of this study, the technology behind it, and its broader implications for public health, businesses, and the real world. And of course, I'll also highlight some similar technologies that could be leveraged across various sectors. The study I'm discussing today focuses on the automatic detection of cooling towers using deep learning models. Cooling towers are standard worldwide for discharging warm air and cooling large buildings such as factories and power plants. Cooling towers are a significant source for Legionnaires' disease, a severe form of pneumonia. When these bacteria grow in cooling towers, they can then be spread through the air, causing outbreaks, especially in densely populated urban areas, near the cooling towers. In the past, locating these cooling towers during an outbreak has been a painstaking manual process, which can be slow and prone to errors. This study introduces a deep learning model designed to detect cooling towers from aerial imagery automatically, significantly speeding up the process and potentially saving lives by preventing the spread of the disease. The researchers set out to create a model that could quickly and accurately identify cooling towers. They used a two-stage deep learning approach, combining two powerful models, YOLO version 5 for object detection and EfficientNet B5 for image classification. Both models are easily accessible through the really excellent Hugging Face platform for any developers wanting to take advantage of them. So let me break down these models for you. The researchers used YOLO version 5, which is up to, I believe, version 9 at this point. And this is an object detection model that scans an image and identifies objects within it. YOLO was created by teaching a computer to recognize different objects in images by showing them extensive examples. YOLO can be extended, like these researchers did for cooling towers, by training a new model with YOLO as its backbone and providing examples of what they were looking for. However, not all detections are perfect. So they introduced a second stage with the EfficientNet B5, a classification model. This second model looks closer at the potential cooling towers identified by the first model, quickly filtering out any false positives or instances where the first model incorrectly identified a cooling tower, and therefore very dramatically improving the detection accuracy. And again, similar to the first model, they train a new model with the EfficientNet model and a few labeled examples of correctly identified cooling towers. In addition, they used a really interesting technique to generate synthetic data, labeling examples as time-consuming. So they took their labeled examples of cooling towers and copy and pasted some of these correct cooling towers onto images of areas that don't have cooling towers. So this is an interesting way that they generated synthetic data to train their model. The combination of these models achieved impressive results. So they had a sensitivity, or the model's ability to correctly identify actual cooling towers, as high as 95.1% in some cities. And it's not just accurate, it's fast. In their tests, the model was over 600 times faster than human investigators at scanning large urban areas. I appreciate that they first report, very promising model evaluation metrics, and second, they compare time saved using the model, against traditional techniques, which is in the end, a primary goal of us using technology. Because they are in the medical domain, they use sensitivity and PPV as their evaluation metrics. These metrics in machine learning are more commonly known as recall and precision. Therefore, their metrics are very solid for accurately detecting cooling towers, minimizing all types of errors. Still, for example, in Boston, their precision of 90.8, which is slightly lower, means that they are detecting slightly more false positives. Again, this is where the model says it's a cooling tower, but actually it's not. In some use cases like this, where the model's saving a lot of time, this only means people are wasting a little bit of time looking at an instance and saying, oh, it's not a cooling tower. However, in other cases, especially when you're taking the machine learning results as entirely trustworthy, you would ideally want both very high precision and recall. Now let's talk a little bit more about the technology that makes this possible. YOLO and EfficientNet are really trusted and heavily used models in their respective areas. YOLO is known for its speed and accuracy in detecting objects in real time, which is crucial when scanning thousands of images. EfficientNet, on the other hand, is a family of convolutional neural networks that balances between accuracy and efficiency, making it ideal for refining the results from YOLO. An additional advantage of using these models is that they are pretty straightforward in how they work, which leads to explainable AI. Explainable AI is a crucial term, especially critical in public health, which means we know how models achieve their results so that decision makers have confidence in their actions. Explainable AI and the concept of some models are black boxes is really critical to address. Still, we cannot fear these concepts too much, because models do not necessarily need to be explainable to everyone, as long as trusted experts can explain them. Think of the analogy that you do not need to know exactly how your car or even your computer works the way it does for you to trust them. This research is a fantastic example of how deep learning can be applied to geospatial data. In my work, I've seen similar models used to detect everything from deforestation to urban growth patterns, and even to predict disease outbreaks based on environmental factors. The beauty of these models is that they can be trained on a wide variety of data, making them incredibly versatile tools in public health and beyond. For example, much of our environment, from mosquito breeding sites to green areas in cities to illegal trash dumps, affects our collective health. Similar computational techniques to what we see here can, in the end, lead to a healthier world. So what does this mean for the future? This research represents a significant step in public health outbreak investigation. By automating the detection of cooling towers, public health officials can respond more quickly to potential Legionnaires disease outbreaks and save lives. But the implications go beyond just public health. Businesses in urban planning, real estate, and environmental monitoring can also benefit from similar technology. For instance, automated detection models could be used to maintain up-to-date infrastructure maps or monitor environmental compliance, such as, in this case, ensuring proper cooling tower maintenance to prevent future outbreaks. Given my extensive experience in AI and geospatial technologies, I'm well equipped to help organizations implement similar solutions. I personally used deep learning on aerial imagery to automatically map buildings and oil spills. Also recently, I collaborated with the World Health Organization using AI on massive environmental and demographic data throughout Africa to understand and predict disease outbreaks at both a high spatial resolution and at the continental scale. Whether it's developing custom models to address specific challenges or optimizing existing data workflows, I can provide the expertise needed to harness the power of AI for your business or public health initiatives. Feel free to reach out if you're interested in exploring how these technologies can be applied to your work. I'm always excited to discuss new projects and challenges. To wrap up, this study is a perfect example of how AI transforms how we approach public health crises. By leveraging deep learning models, we can drastically improve our ability to respond to outbreaks like Legionnaires disease, making our communities safer and healthier. Finally, I'd like to thank the authors for their excellent research contribution. The lead author and also some other authors are affiliated with the U.S. Centers for Disease Control and Prevention in Atlanta, Georgia, and also the University of California at Berkeley in beautiful Berkeley, California, across the bay from San Francisco. And it's nice to see that many of the researchers and the research center at Berkeley are interdisciplinary in their backgrounds, combining the medical experience with technology. Thank you for watching. If you found this video insightful, please like, share, and subscribe for more content on AI, geospatial technology, and their real-world applications. And if you have any questions or ideas, leave them in the comments below, or send me an email or message. I'd love to hear from you.